Hello and welcome to Postdoc Chronicles week number 30. So I am in Kruger right now, attending the international conference called the Discovery Physics at the LHC, and it will be from today, December 3, up to December 7. I have a presentation. I'm giving a talk on tomorrow, December 4, and it's gonna be my first international conference in the field of particle physics. Like as you may know, I shifted from quantum information. So I've joined international conference in quantum information before, but this is the first on particle physics. Okay, so I'm gonna be a talk that will last for 15 minutes, and so I just want to go over my slides and make sure. So I'll present as if I'll be presenting tomorrow, just to make sure that I will be within that 15-minute limit. And if I go over it, then maybe tomorrow I'll go faster. If I'll be under it, then maybe tomorrow I'll go slower, to reach 15 minutes. So let's do this. I have a timer here on my cell phone. I'm going to start it and then I end it. And let's see if it's 15 minutes. Okay, so hello, and my presentation will be is entitled Stealth SUSY Search with a Large Radius Jet Containing a Photon. And I'm Marvin Flores, and I did this research together with Dr. Deepak Kar and Jong-Soo Kim, and I'm from the University of Witwatersrand. Okay, so the flow of my presentation will be as follows. I'm gonna talk about the basics of supersymmetry, or SUSY for short, and then I'll discuss a very specific scenario known as stealth SUSY, and then we will talk about what our specific decay chain is, what we're basically doing with that specific stealth SUSY scenario, and the computational tools that we use, and we're gonna present our results. Right. So SUSY is a theoretical framework that actually introduces one of the problems in the standard model called the hierarchy problem. Okay, so basically in your the mass squared of your Higgs boson, there are loop corrections to it that are contributed by each of the fermions and the bosons that you have. Okay, and the open question is, why does the Higgs boson maintain this small mass even though you have the presence of these corrections? But the funny thing is, when you look at the exact forms of the equations of these loop corrections, the form of the equation looks very the same, but for a difference in sign. Okay, so one is a minus, one is a plus, and so SUSY, does this. You can even say that it's contriving, very very contrived. What it does is introduces, in order to make those corrections cancel for each of that bosonic term, you introduce a fermionic partner, so in order to cancel that term. And so once you introduce a super partner to every existing standard model particle, then that hierarchy problem, that correction to the mh squared, they are made to cancel each other. Okay, and so what we have is, instead of the just the standard particles that we know and love, that we can sort of cook in the CERN, we have this additional super partners known as the SUSY particles. So for example, for the squarks, we have the for the quarks, we have the squarks. For leptons, we have the sleptons, and so on. Okay, so it basically sort of double the existing particles that we do have right now. Okay, and then the problem is, so they are supposed to be symmetric. So for every fermion that we know, there should be a boson partner. For every boson that we know, there should be a fermion partner. But the thing is, we know that since we haven't found these guys yet at CERN, we know that for example, the partner of the electron, which is the selectron, we know that they couldn't be this symmetric after all, because they have different mass. Okay, so the thing is, we know that the SUSY, this symmetry is spontaneously broken. Okay, and so what happens is, SUSY particle can attain masses different to the masses of our standard model particles. And this is the interesting thing that we want to know, is what are these masses, because presumably we know the other properties of the SUSY particles. For example, we know that an electron will have a negative charge, same as this electron. We know that the quarks and gluons are governed by the strong interaction. Similarly with Squark and Gluino, and so on. But we don't know what their masses are. So this is the one of the things that we're trying to put limits on, or to put a benchmark, is how large or how small could this SUSY particle masses be. So now, there are a lot of SUSY particles, but we are going to focus on specific ones called the Neutralinos and the Gravitino, because for the reason that these are the guys that we will be using in our specific model. Okay, so by convention, Neutralinos are given the symbol chi1, and of course the superscript 0 corresponds to the fact that they are neutral, hence the name Neutralino. And of course, by convention, the higher Neutralino have the higher numbers in their subscript. So for example, chi2 is greater than chi1. So chi1 is basically the lightest Neutralino. And these guys are actually the mixings of the super partners, or the mixings of the Bino, Singlino, the neutral Higsinos, and the Wino. So basically, this Wino and Bino, for example, these are the super partners of the usual in the electroweak that we know. So Bino is the super partner of B, and then Wino is the super partner of like the W's, the W bosons that we know, and so on. But these guys are not the ones we see in the experiment, so they undergo a mixing. So these so-called gauge eigenstates are related to the mass eigenstates, which are the neutralinos by some matrix. Okay, and the neutralinos, the chi's, these are what supposedly we are able to measure at the colliders that we have. So another SUSY particle of interest is the gravitino, which is supposedly the super partner of the graviton. Okay, so another standard model particle that we think exists, but we don't know that yet. But according to SUSY, once we find a graviton, okay, it's supposed to have its own super partner known as the gravitino. And again, after SUSY breaking, the gravitino can obtain its own mass. And in specific models of SUSY, in particular the one called GMSB, or the gauge-mediated SUSY breaking model, the gravitino is the so-called lightest SUSY particle, or we called it the LSP. Okay, and so once you are the LSP, since you're the lightest SUSY particle, you can't decay into any other SUSY particles because there's nowhere to go. Okay, so that's the LSP, and in this particular decay chain that we'll be using, we will consider gravitino to be our lightest SUSY particle. So gravitino will be our LSP. So the main problem is we've been doing the experiment in LHC for more than 8 years now, but there's no evidence in favor of SUSY. Okay, and so if you've seen the Pixar film Finding Dory, so if spoilers, they actually were able to find Dory at the end. Okay, but us in CERN, we've been doing these experiments, we've been trying to find SUSY, so that's why I made their Finding SUSY, but we haven't found it. Okay, and so I placed there just keep searching instead of just keep swimming. But yeah, basically, people, advocates of SUSY, they're like, just keep on looking, they'll be there. But yeah, there are other people who are sort of like kind of disappointed, or they're not happy that after 8 years the SUSY has not yet been found. Okay, and they want to change field or something. But yeah, I think it's we all know that is part of the progress of physics, right? I mean, what we're trying to do is, we don't know the specific theory or the specific model that explains the universe right now, and so we have this SUSY. If it turns out to be wrong, then think of me personally, I just think of it as a specific path that specific generation of physicists followed, that turns out to be a dead end. And so it's not really for naught, because it would be something that we won't be followed by future generation of physicists. We've taken that road. We know that it's dangerous. It's a dead end. It doesn't work. Use this path. Okay, so it's still helpful. Okay, but anyway, the thing is, for those who are really hardcore advocates of SUSY, there are still a lot of models that could be saved even with the presence of a lot of Atlas or CMS searches saying that they're not there. Okay, so, and in fact, what these models do is they try to evade the signatures that are being used by Atlas and CMS. So for example, Atlas will look for something like, oh, SUSY is not true, is not correct because we haven't found this ingredient, and then some people say, actually that ingredient, you don't need that in SUSY. Okay, and so there are a lot of those models, but we are going to focus on this thing called the stealth SUSY. So this stealth SUSY, the particular ingredient that it would like to avoid is the missing ET, okay? Because in a lot of searches for this SUSY particles, it relies on the presence of a huge amount of missing ET, okay? And so stealth SUSY, what it does is it now tries to construct a specific decay chain or a specific SUSY model that does not rely on that specific ingredient, which is the missing ET. And what it does is, so it has this thing called the lightest visible sector, okay, or the LVSP, okay. So in our particular case, we will see later, our LVSP will be the lightest neutralino, which is Chi1. And so what it does is that Chi1 will decay into another SUSY particle. In this case will be the Singlino in our particular decay chain, and then that Singlino will decay into a singlet, which is a standard model particle. And so what we do is, in order to have a stealth SUSY, we make sure that the Singlino and the singlet have a very almost the same mass, okay? And so what happens is, since they have almost the same mass, the resulting final product, once the Singlino decays into singlet, since they only have almost the same mass, so you get a very light SUSY particle, LSP, which we assume to be the Gravitino, and this Gravitino is going to be very soft, okay? And so now we just what we're going to do is we forget about the missing ET, because the difference between the Singlino and the singlet will be very small. So what we do is we focus now on the visible products. In this case, the singlet will decay into, for example, gluon, and then we focus on this the remaining visible products in the hopes of finding a resonance or reconstructing a mass distribution that peaks at the SUSY particle that we're trying to reconstruct, okay? And again, for this specific case, we have this decay chain, okay? So we have a squark that would decay into a quark and the lightest neutralino, which is sometimes called Bino-like, but later on in the slides, I'm just gonna call it the Bino, okay? So the Bino will decay into the Bino-like will decay into photon and a Singlino, and then the Singlino will decay into a Gravitino, which is our LSP, and a singlet, and finally that singlet decays into a gluon. And so what we're gonna do is we're trying to reconstruct the lightest neutralino, the Bino, by looking at the products gamma, GG, okay? These are the visible products. We know that the missing ET is gonna be very small. So in fact, what we did first is we attempted actually to reconstruct the squark itself. So look at the visible product Q gamma GG, okay? But then in order to do that, you need to have an ultra obese, ultra fat jet in order to contain everything. And so I was told that in Atlas or CMS, you should have something like R equals 1. When I did the simulation, in order to reconstruct the squark mass, the Q gamma GG, I have to set R greater than 2, so it's gonna be very fat. So we what they call this, we confined ourselves with the reconstructing the Bino, the gamma GG, and in what we did is this a pair production, but we just look at the one side since it's asymmetrical, okay? So we generated the events with that particular decay chain using Pythia and MadGraph. So we modified the decay table, the mass spectrum, in order to accommodate that specific decay chain. And then we select benchmark points, the allowable pairs of Bino and squark mass, by using CheckMATE. So CheckMATE is a tool that checks whether your model is allowed or excluded by existing Atlas and CMS searches. Okay, and then afterwards, we use Rivet to analyze the selected benchmark points and then construct the mass distribution of the jet, which will be composed of gamma GG. Okay, so this is the exclusion plot that is produced by CheckMATE. So we look at Bino masses from 250 to 400 GeV, and then we look at squark masses from 1,400 to 2,000 GeV. All right, and so basically, the once you run CheckMATE, it will give you a number called R. But so basically, when R is less than 1, it's supposed to be allowed, but then if it's greater than 1, it is excluded. But then we have this, region where actually we are not sure. So this has something to do with the uncertainty in the Monte Carlo generation. So we're not sure about the fluctuation and so on. So this is the region of, how should we call it, sort of ignorance or something. So once your value falls here, so maybe CheckMate is allowing it when it should be excluded, or maybe CheckMate it is excluding it when it should be allowed. Okay, so in order to be in the safe region, you should be like less than 0.67, so in the green region. But for our case, we also pick two benchmark points, somewhere in the yellow but near the green one. Yeah, but anyway, basically we have 5 pairs of Beano and Squark masses. Okay, and this is the event selection. So these are the cuts that we use to define our jet. So again, when the events that we want to construct the mass distribution of, it should have at least one large jet from all stable final particles except muons and neutrinos, and then we require it to contain a photon with that specific cuts right there. And then so we have a large radius jet of radius equal to 1, and then whenever a photon is inside it, then we plot its mass distribution. And then for backgrounds, we use Pythia to simulate SM backgrounds comprising of gamma plus jet and then multi-jets. Okay, and then the cross section, when we plotted the mass distribution, it's normalized to the cross section of the signal and the standard model backgrounds, and we used a total integrated luminosity of 150 inverse femtobarns, of course, for I believe this will be the value by the end of run 2. And these are our results. So as you can see, once we run our Rivet analysis, so you can see a mass distribution. You have a resonance that peaks at the value of our Beano mass. So in the first benchmark point, you have a Squark mass of 1,650 and then a Beano mass of 250. So it peaks at around 250. The other one is another benchmark points, but it peaks at around 270. Okay, and similarly for the other benchmark points. So you would notice right away that as you begin to increase the mass of the Squark, the peak of the peak where the number of events where the Beano mass peaks, okay, so like the efficiency, it becomes smaller. Okay, so in other words, if you want it to be more efficient, you get smaller and smaller Squark mass. However, if you get smaller and smaller Squark mass, you run into the danger of that particular value being excluded by CheckMate. Okay, so you have this sweet spot where it's not too high a value where it's going to give you very inefficient peak, but not too low where it's gonna be excluded by CheckMate. Okay, and another thing that we did in order to clean the signal, because it's kind of like other things near the the peak is not so prominent. So what we did is we attempted to enhance or clean the signal by looking at some parameters that we know is correlated or connected to the Beano mass. So for example, we were trying to construct at least one large jet to peak at the Beano mass. So what we did is, since we know that we're trying to reconstruct gamma GG, what if we force it to have 3 jets? Okay, we force it to have 3 jets, and so what happens is you get something like this. You have a in here you get the green distribution. So these are the same distributions. I just plotted them on the left, a log plot, and then on the right is a linear plot. But basically what happens is the peak becomes very prominent at the mass, the value of the Beano mass, however at the expense of it becoming inefficient. Okay, so it's not really very good, because yes, you're cleaning it, but then it's becoming more inefficient. So a work in progress that we're currently doing now is we're now going to use jet substructures, because we have this fat jet, so we can look zoom into the jet inside it, and try to improve the signal efficiency once we apply these jet substructures. But yeah, that's a work in progress. And before I go to the and finish my talk, here's some last minute caveat. Okay, so we were studying 13 TeV for this model, but then just last week we actually found this CMS paper that specifically targets our decay chain, although albeit at the center of mass energy of 70 eV. Okay, but if you look here carefully, this paper actually puts a limit of a squark mass of 1430 GeV at 70 eV center of mass. Okay, so in other words, so note that if you have like some exclusion plots, some benchmark on some combination of masses, if you have those limits at 70 eV, if you do that similar experiment at a higher center of mass energy, for example at 13 TeV, then the limits would even become more stricter. Okay, and so we're confident that this 1430 GeV minimum value for Squark will be even greater had they done the experiment for 13 TeV. But we've looked so far, but we haven't seen it yet. And so another current work in progress that we're doing right now is this particular paper. This is not, so that's why one of the reasons why we also haven't found it right away is this is not yet incorporated in the current CheckMATE framework. So what I'm trying to do now is I'm writing an analysis for this specific paper so that it will be part of CheckMATE. And then there is something that we can do. I'm still trying to understand it, but I was told that I would be able to some sort of extrapolate the ones that we have here for it to work on a 13 TeV scale, even though the experiment has not been done. But yeah, it would be nice if there's an experiment for this. But yeah, we don't have that so far. Okay, but so what happens is, so good thing we did not pick some benchmark points, less than 1430, because at 70 EV that's already excluded. So we picked some values in the higher portion, in the higher regions of the squark mass. And yeah, so again, we don't know whether, for example, the smallest one that we got, the 1650, I think, we don't even know if it will be excluded had the CMS experiment been done at the current energy scale of 13 TeV. Okay, yeah, but basically that's what we've done. So we look at a specific model in SUSY known as the stealth SUSY, where we avoid the missing ET signatures that are being used by LHC. And in doing so, once we have this specific model, we look at their, instead of looking at missing ET, we look at their visible final products, in this case, gamma GG, and then this gamma GG, we attempt to reconstruct, look at their resonances in the attempts of reconstructing this SUSY particles, in our case, the lightest neutralino, or the Bino-like Chi10. Okay, and this has not been done in the experiment so far, where you include a gamma in your GG jet. So I've heard what the is typically done is an electron inside a large jet, but not a gamma inside a large jet. So it would be also interesting in that, from that point of view. Okay, but yeah, basically that's my talk, and so we're good. If I look at the time, I reach like 20 minutes. So I think, yeah, I need to be fast. I need to be a little bit faster in my presentation tomorrow. So I don't know where I'm gonna cut the time, but yeah, I think at least the pace is around 20 minutes, so that should be fine, I guess. But yeah, anyway, so my presentation will be tomorrow, December 4, but the problem is this postdoc chronicles, I don't think so. Basically, last week for this that's why I'm doing this for my postdoc chronicles, is because this is the only thing that I've been doing since last week, preparing for my talk for this specific conference. All right, and so the problem is here right now in Kruger. So currently I'm in my hotel. It's like in the middle of a forest near a sanctuary where you have the safari for wildlife and stuff. And so the internet is not that very good, the internet connection. And so I don't think I can upload this video on YouTube right away. So maybe the time I would be able to upload this on YouTube, it would already be like, I think the conference would have already been concluded. Okay, but still, I'm gonna upload this, and at least I was able to run through my slides. I hope they won't ask me some very heavy loaded questions tomorrow, because like I said, I'm just a beginning researcher in particle physics. But yeah, I'm grasping it so far, and yeah, like my supervisor said, it's really easier to learn when you're doing some actual research. Okay, but yeah, that's it for my Postdoc Chronicles week number 30. And like I said last time, the Postdoc Chronicles week number 31, which hopefully I'm gonna be able to upload by, I don't know, Sunday, December 9, I believe. That's a Sunday. So that's the last Postdoc Chronicles for 2018, because I'm gonna be having a Christmas vacation after that, and of course I won't be doing any Postdoc Chronicles when I'm having my vacation in the Philippines. Okay, but anyway, thank you very much, guys, for watching, and I'll see you next time. Bye bye.